January 5, 1943. USS Helena, Coral Sea, approximately 40 nautical miles northeast of Guadalcanal. Lieutenant Commander Robert "Red" Cochrane wiped sweat from his forehead as he stared at the plotting board in the aft fire control station, trying to make sense of what had just happened. The mathematics don't work. We missed by at least 20 yards. The shells should have continued downrange and detonated on the water or in the air miles beyond the target. But the Val disintegrated. 4 Aichi D-3A Val dive bombers had attacked the task force at 13:47 hours, dropping their payloads and breaking away at full throttle, approximately 200 miles per hour at 1,000 feet altitude. Standard procedure. The Japanese pilots had executed their escape perfectly, jinking and weaving as they raced back toward their base at Munda. Cochrane's battery, 3 Mark 12 5-inch guns, had fired 3 salvos. 9 shells. The second salvo had obliterated one Val in midair, but none of the shells had struck the aircraft. Cochrane examined the radar plot again. The track was clear. The Japanese bomber had been 23 yards from the nearest shell's trajectory when it exploded. 23 yards. In naval gunnery against fast-moving aerial targets, that counted as a clean miss. Except the Val wasn't flying anymore. It was falling into the Pacific in burning fragments, while its 3 companions fled toward the horizon. The other gun crews were celebrating. Cochrane's team had been issued the new Mark 53 ammunition 6 days earlier with explicit orders: do not discuss the shell's capabilities with anyone outside the battery. Do not allow unexploded rounds to fall into enemy hands. If capture seems imminent, destroy all Mark 53 ammunition and associated documentation. The secrecy surrounding these particular shells exceeded anything Cochrane had encountered in 2 years of Pacific combat. Now he understood why. The shells were detonating themselves, somehow, without impact, without timer settings. The projectiles were determining their own optimal burst points based on proximity to the target. The implications staggered him. Every principle of anti-aircraft gunnery he'd learned at Annapolis and refined through dozens of engagements assumed that shells were fundamentally stupid, ballistic projectiles that exploded on contact or at predetermined intervals. These shells were different. These shells were watching. The discovery would eventually be recognized as one of the most significant technological achievements of World War II, ranking alongside radar and the atomic bomb. But on January 5, 1943, as Lieutenant Cochrane watched 3 surviving Vals disappear into the tropical haze, he simply wrote in the battery log, 3 salvos fired, 1 enemy aircraft destroyed. Expenditure Mark 53 ammunition. The Japanese pilots who witnessed their companions' destruction radioed their base with a confused report. American anti-aircraft fire had somehow destroyed an aircraft without direct impact. Their intelligence officers had no explanation. Neither did their German allies, who were observing similar impossible accuracy in European skies. Neither enemy would learn the truth until after their surrender. Each American shell contained a complete miniature radar system that told it exactly when to detonate for maximum lethality. The weapon they faced was invisible, incomprehensible, and devastatingly effective. And the story of how American engineers accomplished what German scientists had declared impossible began 3 years earlier in a Baltimore laboratory driven by a British discovery and an impossible deadline. The journey to Lieutenant Cochrane's bewildering victory began in 1939 at the British research establishment at Bawdsey Manor, where scientists wrestling with the problem of anti-aircraft gunnery reached a disturbing conclusion. Traditional proximity fuses were inadequate. For decades, anti-aircraft shells had used time fuses, mechanical devices set before firing to detonate at a predetermined altitude. Gunners calculated the target's altitude, speed, and direction, then set the fuse accordingly. The system required perfect calculation, perfect timing, and enemy aircraft that cooperated by not changing altitude or direction. Against modern aircraft capable of 300 miles per hour with the ability to dive and climb at will, time fuses achieved kill rates of approximately 1 aircraft destroyed per 10,000 rounds fired. The mathematics were brutally simple. Anti-aircraft defenses were essentially ineffective. British researchers experimented with photoelectric fuses that would detect the change in light intensity as a shell passed near an aircraft. The concept showed promise in laboratory testing but failed catastrophically in field trials. Clouds triggered false detonations. So did the sun. So did the ocean surface. The system couldn't distinguish between an enemy bomber and a seagull. In September 1939, as Britain entered the war, a team led by physicist William Butemant developed a different approach, a miniature radio transmitter receiver that would detect the presence of aircraft through reflected radio waves, essentially a tiny radar system inside each shell. The concept was theoretically sound. The practical challenges were staggering. Any device installed in an artillery shell would endure acceleration forces exceeding 20,000 times Earth's gravity when fired, 20,000 Gs. It would spin at approximately 25,000 revolutions per minute. It would experience temperature swings from -50 degrees Fahrenheit at altitude to over 100 degrees in the gun barrel. And it would need to be small enough to fit inside the fuse cavity of a 5-inch shell, a space roughly the size of a coffee cup, while remaining cheap enough for mass production and reliable enough to function after months in storage aboard ships operating in tropical and Arctic conditions. German scientists conducting parallel research concluded the challenge was insurmountable. The vacuum tubes required for radio transmission would shatter instantly under firing stress. The timing circuits couldn't possibly survive the spin rates. The entire concept violated fundamental principles of electrical engineering. They abandoned proximity fuse development as theoretically interesting but practically impossible. The British, desperate and facing nightly Luftwaffe raids, couldn't afford to accept impossibility. In September 1940, with the Battle of Britain reaching its crescendo, the Tizard mission arrived in Washington carrying Britain's most valuable military secrets, including the cavity magnetron that would revolutionize radar and the preliminary research on proximity fuses. The British essentially handed America their entire scientific war effort with a simple request: you have the industrial capacity we lack. Make this work. The U.S. Navy designated proximity fuse development as their highest priority and assigned the project to the Carnegie Institution's Department of Terrestrial Magnetism in Washington, D.C., under the direction of Dr. Merle A. Tuve. Tuve, a physicist who had helped develop radar before the war, assembled a team at Johns Hopkins University's Applied Physics Laboratory in what became known as Section T. Their deadline was impossibly tight, operational fuses within 18 months. The first challenge was the vacuum tubes. Standard radio tubes of the 1940s were fragile glass bulbs containing delicate internal elements suspended by thin wires. Subject one to 20,000 Gs and it would explode into powder. Tuve's team needed tubes that could survive artillery forces while still functioning as radio transmitters and receivers. The solution came from miniaturization and ruggedization beyond anything previously attempted. Engineers at the National Bureau of Standards developed vacuum tubes smaller than a pencil eraser, with internal elements soldered directly to the tube's structure rather than suspended on wires. Every component was tested to failure under acceleration forces. Designs that couldn't survive 25,000 Gs were rejected and redesigned. By early 1941, the team had produced vacuum tubes that could endure being fired from a gun, tubes that German engineers still believed were physically impossible. The second challenge was power. The fuse needed a battery that could survive the firing shock, occupy minimal space, and provide stable voltage for 15 to 20 seconds, enough time for the shell to reach its target at ranges up to 15,000 yards. Engineers developed a battery activated by the firing shock itself, using the shell's acceleration to break ampules of electrolyte that powered the circuit. The battery literally turned on when fired. The third challenge was the radio system. The fuse would transmit a continuous radio signal and listen for reflections. When the reflected signal strength indicated the shell had approached within 70 feet of a target, the optimal burst radius for the shell's fragmentation pattern, the fuse would trigger detonation. This required a transmitter, receiver, amplifier, and triggering circuit, all occupying the space inside a projectile's nose, all able to process radio signals while spinning at 25,000 RPM. All able to distinguish between aircraft and clouds or ocean surfaces. By December 1941, as America entered the war, Section T had developed a functional prototype. The Mark 53 Variable Time Fuse, the VT designation chosen deliberately to disguise its radar nature, measured 4.5 inches long and 1 3/4 inches in diameter. It contained 4 sub-miniature vacuum tubes, a battery activated by setback force during firing, a radio transmitter operating at 180 MHz, a receiver, an amplifier, and a triggering circuit. Total component count, approximately 70 individual parts. Total weight, 1 pound 4 ounces. The first live test occurred on August 12, 1942, over Chesapeake Bay. The cruiser USS Cleveland fired 4 Mark 53 fused shells at radio-controlled target drones. The test was scheduled for 2 full days of shooting to gather statistical data. It ended in 3 hours because all 3 drones had been destroyed and Cleveland had no more targets. 4 shells, 3 aircraft destroyed. 1 round was a dud, later recovered for analysis. The working fuses had performed perfectly, detonating at optimal range from their targets. The effectiveness increase over time-fused ammunition exceeded 300%. The Navy immediately ordered mass production. The Mark 53 fuse entered combat service in January 1943 aboard cruisers and destroyers operating in the Solomon Islands. The Navy maintained absolute operational security. Gunners received no explanation of how the new ammunition worked, only that it was significantly more effective and was to be used exclusively against aerial targets over water, where unexploded rounds would sink and remain unrecoverable by enemy forces. The results were immediate and dramatic. On January 5, 1943, USS Helena destroyed 1 Val dive bomber with 3 salvos, the engagement that bewildered Lieutenant Commander Cochrane. The following day, January 6th, destroyers USS Nicholas and USS De Haven engaged a formation of 9 G4M Betty bombers attacking near Guadalcanal. 5 salvos, 2 Bettys destroyed, 3 damaged. Pre-VT engagement statistics for similar encounters averaged 1 aircraft destroyed per 37 salvos. January 12, 1943, USS Montpelier engaged 6 Val dive bombers, 4 salvos, 2 Vals destroyed. January 19, USS Columbia, 8 Vals, 6 salvos, 3 destroyed. The pattern was unmistakable to anyone analyzing the combat reports. American anti-aircraft effectiveness had increased by a factor of 3 or more. But only Navy intelligence analysts saw the complete picture. Individual ships simply knew their gunnery had become remarkably effective. The Japanese noticed. Intelligence reports from captured documents and interrogated prisoners indicated growing confusion about American anti-aircraft capabilities. One report from Rabaul dated February 1943 noted that American naval gunfire achieves detonations in proximity to aircraft without apparent impact, cause unknown, possibly advanced fire control radar. The Japanese analysis was half right. American fire control radar had improved substantially by 1943, but radar-directed gunfire still required time-fused ammunition that burst at predetermined altitudes. What the Japanese were witnessing wasn't better aiming, it was shells that aimed themselves at the last possible moment. By mid-1943, VT-fused ammunition constituted approximately 25% of anti-aircraft rounds issued to the Pacific Fleet. These rounds accounted for 50% of all Japanese aircraft destroyed by naval gunfire. The mathematics told the story. VT fuses were 3 times as effective as conventional ammunition. But the Navy couldn't deploy VT fuses universally. Production limitations restricted supply, and operational security demanded that conventional time-fused ammunition remain in use to avoid alerting the enemy that a revolutionary weapon was in play. The restrictions were absolute. VT-fused shells could only be fired over water, where unexploded rounds and fragments would sink. They could only be used against aerial targets, never for shore bombardment, where the Japanese might recover intact fuses. Ships carried VT ammunition in secured magazines with guards posted. Gunnery officers received court-martial threats if they violated the protocols. The secrecy was necessary because the implications of the technology extended far beyond anti-aircraft warfare. If the Germans or Japanese recovered an intact VT fuse and reverse-engineered the components, they would understand that American industry had solved the miniaturization problem for electronics. They would realize that Americans could build ruggedized miniature devices capable of surviving extreme forces. They would begin developing their own smart weapons. But through 1943 and into 1944, neither enemy realized what they faced. The Japanese attributed American accuracy to superior training and better radar fire control systems, technology they understood. German intelligence officers, analyzing reports from Japanese sources and from Luftwaffe crews encountering U.S. Navy vessels in European waters, reached the same conclusion. American gunnery had improved through better equipment and training, not through revolutionary weapons technology. The pattern continued. Every month brought new combat reports demonstrating VT fuse effectiveness. USS Birmingham, March 1943, 4 salvos, 2 Bettys destroyed. USS Nashville, April 1943, 5 salvos, 3 Vals destroyed. USS San Diego, June 1943, 11 salvos, 7 Zeros and Vals destroyed or damaged. The statistics accumulated. By the end of 1943, Ships equipped with VT-fused ammunition were destroying Japanese aircraft at rates 5 times higher than ships using conventional ammunition. But the advantage depended entirely on absolute secrecy. The moment an intact fuse fell into enemy hands, the weapon's effectiveness would be compromised. The Japanese would develop countermeasures. They would pursue their own proximity fuse development. They might even learn enough about American electronics manufacturing to understand broader capabilities they could exploit or counter. Therefore, through 18 months of combat, not a single VT fuse could be allowed to reach enemy territory intact. Every shell fired over land was conventional. Every round fired over shallow water where enemy divers might recover it was conventional. The most effective anti-aircraft weapon in the American arsenal could only be used under conditions that guaranteed its security. That restriction was about to change. But by mid-1944, the tactical picture demanded revision of the absolute security protocols. The war in Europe was entering its climactic phase. The Normandy invasion in June had established a foothold on the continent, but German resistance remained fierce. The Luftwaffe, though weakened, still posed significant threats to Allied forces. And German V-1 flying bombs, primitive cruise missiles, were striking London with devastating effect. The V-1 presented a unique challenge. Unlike conventional aircraft, the V-1 flew at constant altitude and speed, approximately 400 miles per hour at 2,000 to 3,000 feet. No pilot meant no evasive maneuvers. The V-1 was an ideal target for proximity-fused anti-aircraft fire. But using VT fuses over England meant accepting the risk that unexploded rounds would fall on British soil, where German agents might recover them. The British made the calculation. The V-1 attacks were causing substantial civilian casualties and damage. Conventional anti-aircraft fire was destroying approximately 24% of V-1s that entered the defense zone. Initial tests with VT-fused ammunition increased that to 79%. In late June 1944, British anti-aircraft batteries received authorization to use VT ammunition against V-1s. Within weeks, the effectiveness rate climbed to 86%. German intelligence recovered fragments of VT fuses from British soil. By August 1944, German engineers understood that Americans had developed proximity-detonating shells. But the damage was contained. The Germans had already lost air superiority. Their electronics industry lacked the capacity to develop countermeasures or matching technology. And crucially, they had dismissed proximity fuses as impossible years earlier, which meant they had no foundation for rapid development even if resources had been available. The revelation that Americans possessed working proximity fuses was operationally insignificant at that stage of the European War. The technology's existence changed nothing about German capabilities or tactics. The shells simply continued destroying German aircraft and V-1s at extraordinary rates. But the real revolution came in December 1944, when General Dwight D. Eisenhower requested permission to use VT-fused artillery shells for ground support during the Battle of the Bulge. The German Ardennes Offensive, launched December 16, 1944, caught Allied forces off guard. German forces drove deep into American lines, creating a dangerous bulge in the front and threatening the vital supply port of Antwerp. The weather was abysmal, heavy cloud cover preventing air support. American artillery became the primary means of stopping German armor and infantry. Traditional artillery doctrine used impact fuses for direct hits or time fuses for air bursts. Both required precise fire control. VT fuses offered a third option, shells that would automatically detonate at optimal height above the ground, showering German forces with shrapnel regardless of the exact range calculation. Every shell became an airburst without requiring the gunner to set the fuse. Eisenhower argued that the operational advantage outweighed the security risk. If the Germans overran American positions and recovered VT fuses, it wouldn't matter. The Wehrmacht was already defeated. Only the timeline remained uncertain. But the immediate tactical benefit of VT-fused artillery might be decisive in containing the German offensive. On December 24, 1944, American artillery batteries received authorization to use VT fuses for ground support. The results were catastrophic for German forces. The battle for Bastogne demonstrated the weapon's effectiveness. American artillery positions surrounding the besieged town fired approximately 200,000 VT-fused shells into German formations during the final week of December. The shells detonated 15 to 30 feet above the ground, creating overlapping fragmentation patterns that left German soldiers with nowhere to hide. Foxholes offered no protection against overhead bursts. Armor was vulnerable from above. Infantry caught in the open were shredded. General George S. Patton, whose Third Army spearheaded the relief of Bastogne, later wrote, "The new shell with the funny fuse is devastating. I think that when all armies get this shell, we will have to devise some new method of warfare." He credited VT fuses with saving the city of Liège from German capture, and stated that the technology required a complete revision of land warfare tactics. German soldiers who survived the artillery barrages reported experiences unlike any previous combat. Sergeant Hans Weber, 26th Volksgrenadier Division, interviewed after his capture on January 3, 1945, stated, "The American shells exploded above us. We could not understand how they knew the exact height to detonate. We thought they had observers who could see us in our positions. But the shells exploded perfectly, even in fog and darkness. It was like they could see through the weather." The Germans never understood that each shell contained its own sensor determining optimal burst height based on the ground's proximity detected through radio reflection. They attributed the effectiveness to superior American artillery doctrine and training, never suspecting the shells themselves were intelligent. By January 1945, the Battle of the Bulge had ended in German defeat. American forces had reclaimed all lost territory. The Wehrmacht had suffered approximately 100,000 casualties, losses it could not replace. And a significant portion of those casualties resulted directly from VT-fused artillery. The examination of VT fuse fragments recovered by German forces revealed sophisticated miniaturized electronics, but German engineers were baffled by specific details. The vacuum tubes were unlike any they had seen, far smaller and more robust than conventional designs. The triggering circuit appeared to use radio frequency components, but the exact mechanism wasn't clear from fragments. One German report concluded, "The Americans have achieved miniaturization of electronic components beyond our current capabilities. The implications for other weapon systems are concerning, but cannot be assessed without intact examples." The assessment was accurate, but too late. Germany surrendered in May 1945. German engineers never developed countermeasures. The VT fuse had fundamentally altered anti-aircraft warfare and land artillery, and the enemy never understood the full scope of what they faced. Meanwhile, in the Pacific, Japanese forces remained completely ignorant of proximity fuse technology. They continued attributing American anti-aircraft effectiveness to superior training and equipment. That ignorance would persist until their surrender in August 1945. The journey to operational VT fuses began with requirements issued by the U.S. Navy's Bureau of Ordnance in early 1940, following the transfer of British research data. The specifications were precise and appeared mutually contradictory. The fuse must fit within the standard nose cavity of 5-inch 38 caliber naval shells. Maximum dimensions: 4½ inches long, 1¾ inches diameter. The fuse must survive firing acceleration of 20,000 Gs for the first 15 milliseconds, then spin stabilization at 25,000 revolutions per minute for up to 25 seconds. It must function reliably in temperatures from -50 degrees Fahrenheit to 100 degrees above zero. It must resist humidity, salt spray, and vibration during months of storage aboard ships. It must be safe during handling and loading. It must detonate the shell's main charge within milliseconds of detecting an aircraft within optimal burst radius, approximately 70 feet. And it must cost less than $50 per unit, about $700 in modern currency, to enable mass production of millions of fuses. The requirements were simultaneously essential and seemingly impossible. Dr. Merle Tuve, appointed director of Section T at Johns Hopkins Applied Physics Laboratory, assembled a team of physicists, electrical engineers, and mechanical designers. They faced the problem systematically, breaking the impossible challenge into components that might individually be solvable. The first issue was power. Any electronic device requires electricity. Batteries in 1940 were relatively fragile, glass ampules of acid that would shatter under artillery forces. The team developed a battery activated by firing acceleration. The shell's sudden acceleration would crush thin glass ampules containing electrolyte, which would mix with electrode materials and generate voltage. The battery literally turned on when fired. This solved the power storage problem. No active chemicals meant no degradation during storage. The second issue was the vacuum tubes. Radio transmission and reception in 1940 required vacuum tubes, glass envelopes containing heated cathodes that emitted electrons, anodes that collected them, and grids that controlled the electron flow. Standard radio tubes of the era measured 2 to 4 inches long and contained internal elements suspended on thin wires. Subject them to even 10 Gs of acceleration and the wires would snap. 20,000 Gs would transform the tube into powder. The National Bureau of Standards took responsibility for vacuum tube development. Engineers redesigned tubes from first principles. Instead of suspended internal elements, they soldered everything directly to the tube's base structure. Instead of large glass envelopes, they created tubes smaller than a pinky finger. Instead of conventional cathode heaters requiring seconds to warm up, they designed instant-on cathodes that reached operating temperature in milliseconds. The resulting tubes, designated types 2D21, 2E26, and others, looked nothing like conventional radio tubes. They resembled small thimbles with electrical contacts at the base. Testing was brutal. Each tube design underwent centrifuge testing to 25,000 Gs. Designs that survived were test-fired in special artillery pieces instrumented to record the tube's electrical characteristics during and after firing. Failure rate needed to be below 10%. Any design with higher failure rates was rejected and redesigned. By mid-1941, Section T possessed vacuum tubes that could survive artillery forces while still functioning as radio components, tubes that German engineers continued to believe were physically impossible. The third issue was the radio circuit. The fuse would function as a miniature radar, transmitting a continuous signal at approximately 180 megahertz and listening for reflections. When the reflected signal strength indicated proximity to a large metal object, the circuit would trigger detonation. This required a transmitter, receiver, amplifier, and thyratron tube, the triggering component, all functioning while spinning at 25,000 RPM. The mathematics were brutally simple. Radio signals reflect from metal surfaces. An aircraft approaching a shell would reflect an increasingly strong signal as the distance decreased. By comparing transmitted and received signal strength, the circuit could calculate when the aircraft was within burst radius. The challenge was building circuits compact enough to fit in the fuse cavity, robust enough to survive firing, and sensitive enough to distinguish aircraft from clouds or ocean surfaces. Engineer Harry Diamond and his team at the National Bureau of Standards developed miniaturized radio components, capacitors the size of pencil erasers, resistors built into the circuit board itself, coils wound from wire finer than human hair. Every component was tested to failure. The final circuit contained approximately 70 individual parts, occupying a space smaller than a coffee cup. The decision to use radio frequency proximity detection rather than other methods was deliberate. Optical systems couldn't function through clouds or smoke. Acoustic systems were defeated by the shell's own noise. Magnetic detection lacked range. Radio offered the only viable solution, despite the apparent impossibility of fitting a radio in a shell. Dr. Tuve and his team made the decision that would define the VT fuse throughout its service life. They prioritized reliability over sophistication. The fuse would use a simple continuous wave transmission rather than pulsed radar. It would have no discrimination between friend and foe. It detonated near any large metal object. It would be single-use with no safety mechanisms beyond the arming distance of approximately 300 yards from the gun. These limitations were acceptable because the alternative, no proximity fuse at all, meant accepting continued ineffectiveness of anti-aircraft fire. The final design, designated Mark 53, contained 4 miniature vacuum tubes, a battery activated by firing shock, a radio transmitter, a receiver, an amplifier, a thyratron triggering tube, and approximately 60 additional components, including capacitors, resistors, coils, and the detonator itself. Total weight, 1 pound, 4 ounces. Length, 4.5 inches. Diameter, 1 3/4 inches. It fit perfectly in a 5-inch shell's fuse cavity. Production began in late 1941. The Crosley Corporation in Cincinnati, manufacturers of radio components and appliances, received initial contracts in October 1941. Their expertise in mass-producing electrical devices made them ideal for scaling up from laboratory prototypes to industrial production. Crosley delivered their first accepted fuses in September 1942, less than 1 year from contract to production, an extraordinary timeline for a revolutionary weapon. By war's end, production involved over 100 factories and 87 different firms. Sylvania employed 10,000 workers, mostly women, producing 1 million miniature vacuum tubes every 2.5 days, 2/3 the production rate of the entire American radio industry before the war. Total production exceeded 22 million VT fuses at a cost surpassing $1 billion in 1940s currency, approximately $15 billion in modern terms. The VT proximity fuse was not poorly designed. It was brilliantly designed to achieve specific goals: detect aircraft, trigger detonation at optimal range, survive artillery forces, remain simple enough for mass production, and maintain reliability under combat conditions. Those goals did not include being recoverable by the enemy, which explains the absolute security protocols. The design philosophy succeeded completely. The VT Proximity Fuze's combat debut in January 1943 marked the beginning of a systematic transformation in anti-aircraft warfare. The statistics told a story of technological advantage translating directly into Japanese casualties. February 14, 1943, USS St. Louis engaged 8 Betty bombers attacking shipping near Rendova Island. 6 salvos, 3 Bettys destroyed, 2 damaged. Total ammunition expenditure, 18 VT fused shells. Pre-VT statistics for similar engagements averaged 45 shells per aircraft destroyed. March 7, 1943, USS Birmingham, 7 Val dive bombers, 4 salvos, 2 Vals destroyed outright, 3 so heavily damaged they crashed before reaching their base. 12 shells fired. Later analysis of combat camera footage showed that none of the shells had directly impacted the aircraft. All kills resulted from proximity bursts. April 18, 1943, Operation Vengeance, the assassination of Admiral Izoruku Yamamoto. While P-38 Lightning fighters received credit for shooting down Yamamoto's transport aircraft, the mission succeeded partly because VT-fused anti-aircraft fire from naval vessels near Bougainville kept Japanese fighter cover suppressed, preventing reinforcement of Yamamoto's escort. The pattern repeated across every major Pacific engagement through 1943 and 1944. Ships equipped with VT ammunition consistently achieved kill rates 3 to 6 times higher than ships using conventional time-fused rounds. The Japanese noticed the pattern but drew incorrect conclusions. A captured Japanese intelligence document from June 1943 stated, "American naval gunnery effectiveness has increased substantially. Possible causes: improved fire control radar allowing more accurate altitude and range prediction, better training of gun crews, improved ammunition quality. Recommend enhanced evasive maneuvers and increased attack speed to reduce exposure time." The recommended countermeasures were ineffective because they addressed the wrong problem. The Japanese believed American gunners were getting better at calculating where aircraft would be. In reality, American shells were determining their own detonation points independently of the gunner's calculations. Evasive maneuvers didn't matter when the shell adjusted its burst point automatically. Speed didn't help when the fuse detected the aircraft's presence regardless of velocity. By 1944, as American forces pushed closer to Japan, kamikazes replaced conventional bombing tactics. The suicide aircraft presented ideal targets for VT fuses, aircraft flying directly at ships with no evasive maneuvers, determined to close regardless of defensive fire. VT fuses devastated kamikaze attacks. October 24, 1944, Battle of Leyte Gulf. The escort carrier USS St. Lo and her task group faced coordinated kamikaze attacks. 47 kamikazes approached the formation. 31 were destroyed by anti-aircraft fire before reaching the fleet. The 18 ships of the escort carrier group collectively expended approximately 800 VT-fused shells during the engagement, an average of 25 shells per aircraft destroyed. Pre-VT statistics averaged 200 shells per kill. November 25, 1944, kamikaze attacks on Ulithi Atoll. USS Essex and USS Ticonderoga engaged 15 kamikazes. 12 were destroyed by VT-fused fire. The remaining 3 crashed into ships, but 2 were so heavily damaged by proximity bursts that they inflicted minimal damage. Gunnery officers noted that shells appeared to track the kamikazes, detonating precisely when the aircraft entered the fragmentation radius. The Japanese kamikaze pilots never understood why American anti-aircraft fire was so precisely deadly. Training materials recovered after the war showed that Japanese instructors taught kamikaze pilots to expect 20 to 30% losses from anti-aircraft fire based on 1942-1943 statistics. By 1945, actual kamikaze loss rates exceeded 70%. The training was obsolete, but Japanese intelligence never identified the cause. The mathematics of attrition were stark. During 1944, American ships in the Pacific fired approximately 3.8 million rounds of 5-inch anti-aircraft ammunition. Approximately 25%, 950,000 rounds, contained VT fuses. These rounds accounted for approximately 50% of all Japanese aircraft destroyed by naval gunfire that year. The other 75% of ammunition, conventional time-fused shells, accounted for the remaining 50% of kills. The efficiency difference was staggering. VT-fused rounds were 3 times as effective per shell as conventional ammunition. Yet the Navy couldn't deploy VT fuses universally due to production limitations and security concerns. The result was a hybrid approach where ships carried both types of ammunition and used VT rounds selectively for critical engagements. In Europe, the statistics were equally dramatic. British anti-aircraft batteries defending against V-1 flying bombs achieved kill rates of 24% using conventional ammunition through June 1944. After receiving VT-fused ammunition in late June, effectiveness climbed to 79% within days and reached 86% by August. Approximately 1,400 V-1s were destroyed by VT-fused anti-aircraft fire between late June and September 1944, roughly 1,000 more than would have been destroyed using conventional ammunition. Each V-1 that reached London typically killed 6 people and destroyed or damaged dozens of structures. The VT fuse prevented an estimated 6,000 civilian casualties in Britain. During the Battle of the Bulge, the land warfare application proved equally devastating. American artillery batteries fired approximately 200,000 VT-fused shells during December 1944 and January 1945. German casualty reports captured after the battle indicated that artillery caused approximately 60% of their mocked casualties during the engagement, substantially higher than the 30 to 40% typical of previous battles. German soldiers attributed this to better American fire control and increased ammunition expenditure, never suspecting the shells themselves had fundamentally changed. One German after-action report from 12th SS Panzer Division stated, "American artillery has achieved unprecedented accuracy with airburst shells. Recommend infantry avoid concentration in open terrain. Foxholes provide inadequate protection against overhead bursts. Casualties per bombardment have doubled compared to Normandy fighting." The assessment was accurate but incomplete. Casualties hadn't doubled because American artillery was better aimed. They doubled because VT fuses ensured that every shell became an optimally positioned airburst regardless of range calculation accuracy. By early 1945, VT fuse production had reached approximately 1 million units per month. Nearly every American artillery piece and naval gun could fire VT-fused ammunition. The technology had been cleared for use over land following the Battle of the Bulge. Security concerns had diminished. Both Germany and Japan were clearly defeated, and even if they recovered fuses, they lacked the industrial capacity to develop countermeasures or matching weapons. The final statistics compiled after the war quantified the weapon's impact. 22 million VT fuses produced between 1942 and 1945. Approximately 110 factories and 87 firms involved in production. Over 10,000 workers at Sylvania alone producing miniature vacuum tubes. Total program cost exceeding $1 billion, equivalent to approximately $15 billion in 2020's currency. Combat effectiveness. VT-fused anti-aircraft ammunition achieved kill rates 300 to 600% higher than conventional ammunition depending on circumstances. Ships equipped with VT rounds destroyed Japanese aircraft at 5 times the rate of ships using conventional ammunition. Anti-aircraft batteries using VT ammunition against V-1 flying bombs were 3.6 times as effective as batteries using conventional rounds. Land warfare effectiveness. Artillery units using VT fuses inflicted approximately double the casualties per shell fired compared to conventional impact or time-fused ammunition. The effectiveness was highest against infantry and unarmored vehicles in open terrain. Despite these remarkable statistics, approximately 30% of VT fuses were duds. They failed to detonate properly due to manufacturing defects, component failures, or damage during storage and handling. A 70% reliability rate would have been considered unacceptable for most military systems. For VT fuses, even with 30% failures, the weapon remained 3 to 6 times as effective as conventional ammunition. The mathematics were irrefutable. A weapon that worked 70% of the time and was 5 times as effective when it worked still outperformed conventional weapons by a factor of 3. The human cost of this technological advantage appeared in Japanese casualty figures. Air crew losses in 1944 to 1945 exceeded sustainable rates. Experienced pilots who survived missions reported that American anti-aircraft fire had become impossible to evade. Several pilots interviewed after the war stated they believed American shells were somehow guided. An accurate assessment they dismissed as impossible because they had no framework for understanding proximity-fused weapons. The VT fuse contributed directly to Japan's decision to adopt kamikaze tactics. When conventional attacks resulted in 70 to 80% losses before reaching targets, suicide attacks that guaranteed target impact seemed strategically rational. The Japanese never realized that the defensive fire destroying their conventional bombers used the same technology that would devastate their kamikazes. The tactical shift from conventional bombing to suicide attacks changed nothing about American defensive effectiveness. VT fuses killed both with equal efficiency. Production of VT fuses spanned from September 1942 to August 1945. Total production exceeded 22 million units across multiple variants designed for different weapon systems. The Mark 53 represented the initial naval variant designed for 5-inch 38 caliber guns. Length 4 1/2 inches, diameter 1 3/4 inches, weight 1 pound 4 ounces, radio frequency 180 megahertz, detection radius approximately 70 feet, burst pattern optimized for fragmentation against aircraft. Production began September 1942. Total produced approximately 14 million units. The Mark 55 variant, introduced in mid-1943, featured improved moisture resistance for extended storage in tropical conditions. Chemical composition of the battery electrolyte was modified to reduce corrosion. Vacuum tube seals were enhanced. otherwise identical to Mark 53 specifications. Production, approximately 2 million units. The T-95 variant, developed for U.S. Army anti-aircraft artillery, fitted 3-inch guns used by ground-based batteries. Slightly smaller dimensions to accommodate the smaller shell cavity. Same basic circuit design with reduced detection radius, approximately 50 feet, appropriate for the smaller fragmentation pattern of 3-inch shells. Production began January 1944. Total produced approximately 4 million units. The T-96 variant for 90mm anti-aircraft guns represented the most sophisticated version. Larger size allowed additional refinements, including better signal processing and enhanced discrimination against ground returns when used in land warfare. This variant proved particularly effective during the Battle of the Bulge. Production began October 1944. Total produced approximately 2 million units. Loss rates for VT-fused ammunition were negligible. The fuses were consumed upon firing, either functioning successfully or failing as duds. The security concern wasn't battlefield losses, but rather unexploded rounds that might fall into enemy hands. Through 1943 and into mid-1944, approximately 98% of VT-fused rounds were fired over water, where unexploded shells would sink and remain unrecoverable. After authorization for land use in December 1944, approximately 150,000 unexploded VT-fused shells fell on European and Pacific battlefields. Of these, German and Japanese forces recovered approximately 2,000 intact or partially intact fuses for examination. German technical intelligence examined recovered fuses beginning in August 1944. Their reports expressed amazement at the miniaturization achieved, but concluded accurately that German industry lacked the capacity to replicate the technology. One report stated, "The components represent manufacturing precision beyond current capabilities. The vacuum tubes in particular show design innovations we have not previously encountered. Estimated time to develop equivalent technology, 18 to 24 months with unlimited resources. Current resource availability, inadequate." Japanese forces recovered fewer fuses, approximately 300 intact examples between January and August 1945. Japanese technical intelligence recognized the radio frequency components, but struggled to understand the complete circuit. A report dated July 1945 concluded, "American proximity fuse uses radio detection principle. Components are miniaturized beyond our current production methods. Strategic implications are severe. American electronics manufacturing capability exceeds estimates. Recommend immediate development of countermeasures." The report was filed 3 weeks before Japan's surrender. No countermeasures were developed. The comparative analysis with Allied and Axis anti-aircraft technology revealed the VT fuse's revolutionary nature. British anti-aircraft shells through 1943 used time fuses exclusively. German 88mm and 105mm anti-aircraft guns similarly relied on time-fused ammunition throughout the war. Soviet anti-aircraft artillery used time fuses and impact fuses, never developing proximity technology. The Japanese never moved beyond time fuses for anti-aircraft work. The philosophical difference was stark. Allied, particularly American doctrine, prioritized effectiveness, even at high cost. A shell that cost $50 but achieved 300% better effectiveness represented good value. Axis doctrine, particularly German and Japanese, prioritized production volume and reliability over sophistication. German 88mm shells cost approximately $5 per round to manufacture. They were reliable, simple, and produced in enormous quantities. But they required precise fire control calculations and achieved kill rates 1/5 that of VT-fused ammunition. The mathematical trade-off favored the Allied approach. One VT-fused shell costing $50 that achieved a 300% effectiveness increase outperformed 10 conventional shells costing $5 each. The total ammunition weight, storage space, and transportation burden were lower for the more expensive but vastly more effective ammunition. American forces fired approximately 3.8 million 5-inch anti-aircraft rounds in 1944, of which 25%, 950,000, contained VT fuses. Had the entire expenditure been VT fused, Japanese aircraft losses would have approximately doubled, but production limitations and initial security concerns prevented universal deployment until late 1944. By 1945, VT fuse production capacity exceeded demand. Monthly production reached approximately 1.2 million units, while monthly consumption averaged 900,000. The surplus allowed universal deployment. By July 1945, virtually all American anti-aircraft ammunition issued to forward units contained VT fuses. The final battles of the Pacific War demonstrated the weapon's mature effectiveness. July 24, 1945. The naval bombardment preceding the planned invasion of Kyushu. American battleships and cruisers engaged Japanese aircraft attempting to attack the fleet. 438 Japanese aircraft participated in the attacks. 389 were destroyed before reaching the fleet. Anti-aircraft fire accounted for approximately 290 of these kills, a 75% effectiveness rate that would have been impossible without VT fuses. The Japanese pilots who survived reported that American anti-aircraft fire created an impossible wall of explosions. Several stated they believed survival was impossible and expected death during the attack run. The psychological impact was significant. Even suicide attackers expected some chance of reaching their targets. VT fuses reduced that chance to nearly zero. August 15, 1945. Japan surrendered. The planned invasion of the home islands, which would have involved the most intensive use of VT-fused ammunition in the war, never occurred. Stockpiles of VT fuses numbered approximately 8.4 million units at war's end. These were gradually expended in post-war testing or disassembled for component recovery. The program's total cost of $1 billion in 1940s currency, $15 billion now, represented approximately 0.3% of total American military expenditure during World War II. The Manhattan Project, for comparison, cost approximately $2 billion. Radar development cost approximately $3 billion. The VT proximity fuse was the third most expensive Allied technical program of the war, behind radar and atomic weapons, and ahead of advanced aircraft development. The return on investment was measurable. Enemy aircraft destroyed per dollar spent on VT fuses exceeded enemy aircraft destroyed per dollar spent on fighter aircraft by approximately 40% when accounting for pilot training costs, maintenance, and fuel. The VT fuse was not merely effective, it was cost-effective in a way few weapon systems achieve. The examination of VT fuse fragments at technical intelligence facilities in 1945 provided the final accounting of what Japanese and German forces had faced. Engineers analyzing the miniature vacuum tubes, the compact radio circuits, and the shock-resistant construction reached the same conclusion. This represented a fundamental leap in electronics manufacturing that neither Axis power had achieved. A British intelligence officer, examining captured German technical reports about VT fuses in September 1945, noted in his assessment, German engineers understood what they were looking at, but could not comprehend how it had been manufactured. The gap between conception and production defeated them completely. They knew Americans had solved problems they considered unsolvable, but they never understood how. The Japanese response was simpler. A captured intelligence document dated August 10, 1945, 5 days before surrender, contained a technical analysis of recovered VT fuse components, with a final line, "We did not know such things were possible." The VT proximity fuse was not poorly designed. It was brilliantly designed to achieve specific goals: destroy enemy aircraft, survive artillery forces, function reliably under combat conditions, and remain simple enough for mass production. Those goals did not include being understandable to the enemy. The weapon's very sophistication made it invisible. Japanese and German forces saw the effects but could not comprehend the cause. The philosophical lesson extended beyond the specific technology. The VT proximity fuse demonstrated that the most devastating weapons are not always the most visible. The atomic bomb ended the war with obvious, unmistakable destructive power. Radar allowed detecting and tracking of enemy forces with clear strategic benefits. The VT proximity fuse did neither. It simply made existing weapons more effective in ways the enemy couldn't perceive or counter. General George Patton's assessment proved prophetic. The funny fuse required a complete revision of warfare tactics. But the revision wasn't in how to use the weapon. It was in understanding that technological superiority could be achieved through making conventional weapons incrementally but decisively better, rather than developing entirely new weapon types. A shell that detonated automatically at optimal range wasn't a new weapon, it was a better shell. That conceptual distinction mattered. Post-war military development embraced the lesson. Smart weapons, precision-guided munitions, and autonomous systems all followed the VT fuse's pattern. Take existing weapons and make them intelligent enough to optimize their own employment. Modern missiles that adjust their trajectory in flight, bombs that steer themselves to targets, and artillery shells that correct their path mid-flight are all descendants of the proximity fuse's fundamental insight: build intelligence into the weapon itself. The VT fuse remained classified until 1950, when the Navy finally acknowledged its existence publicly. By then, the technology had evolved. Radio frequency proximity fuses had been joined by optical, acoustic, and magnetic variants. The basic principle remained unchanged: detect the target, calculate optimal burst distance, detonate automatically. The fuses used in modern warfare are far more sophisticated than the 1943 Mark 53. They can distinguish between different target types, ignore decoys, and coordinate with other weapon systems. They contain computer chips more powerful than the entire Section T laboratory's computing capacity. But the fundamental concept, a sensor that tells the weapon when to detonate for maximum effectiveness, remains identical to what Dr. Merle Tuve's team developed in Baltimore laboratories 80 years ago. The final irony is that the weapon remained invisible even after the war. Public consciousness fixated on atomic bombs, radar, and aircraft carriers as the decisive technologies. The proximity fuse, which increased anti-aircraft effectiveness by 300 to 600% and fundamentally transformed land artillery, remained obscure. Military historians recognized its significance, but popular history largely ignored it. A weapon that saved thousands of Allied lives and killed tens of thousands of enemy forces remained unknown because it worked invisibly, one shell at a time, with effects attributed to better training or fire control rather than revolutionary technology. The lesson persists in modern military development. The most effective advantages are those your adversary doesn't know exist. Stealth technology renders aircraft invisible to radar. Cyber warfare attacks infrastructure the enemy doesn't know is vulnerable. Electronic warfare jams communications without the enemy understanding what's interfering. These are all descendants of the VT fuze's central principle. Fight with capabilities your enemy can't perceive, counter, or comprehend. On January 5, 1943, when Lieutenant Commander Robert Cochrane watched a Japanese Val dive bomber explode without being hit by his shells, he witnessed the future of warfare. Autonomous weapons making split-second decisions faster and better than any human gunner. The shells he fired that day carried computers, primitive by modern standards, but computers nonetheless that sensed their environment and acted on that information without human intervention. 80 years later, that same principle guides missile defense systems, drone warfare, and precision strike weapons. The technology has evolved beyond recognition. The fundamental concept remains unchanged. And the lesson remains as relevant as ever. The most decisive advantages in warfare are those the enemy doesn't even know to look for. Advantages so seamlessly integrated into conventional systems that they seem like natural improvements rather than revolutionary capabilities. The VT proximity fuse destroyed aircraft, saved cities, transformed tactics, and remained invisible to the enemy until after their defeat. It proved that technological superiority combined with absolute operational security creates advantages that cannot be countered because they cannot be understood. That principle shaped World War II. It continues shaping warfare today. And the story of the funny fuse that confused Lieutenant Commander Cochrane in 1943 remains the template for how invisible technological advantages transform the nature of combat without the enemy ever understanding why they're losing.